Hello, everyone, and thanks for staying for this session. As the title implies, we'll be talking about migrating from C to Rust, both at a strategic perspective, so you will go about approaching such a project, as well as the tactical little challenges that you may find as you try to rewrite C modules over to Rust. Before we get started, let's get introduced. My name is Luca Palmieri, and I work as a principal engineering consultant for Mainmatter, consultancy based in Europe, which, among other things, does Rust consulting. I have personally been in the Rust community for 7 years, but I'm probably best known as the author of Zero to Production in Rust, a book that introduces you to backend development. I'm also working on a new backend framework, which you can find there. Go check it out. We don't have time for details. Let's get to the meat. Everything we'll be talking about happens in the context of Redis. You may know Redis as a key value engine in memory, usually used for caching, queuing, and other use cases. What fewer people do know is that Redis, over the years, has started to distribute additional extensions or modules, which build on top of the key value store to provide different functionality. Redis query engine, in particular, allows you to define indexes over your key value store, which you can then query with what looks like very similar to relational, non-relational queries you might do in Postgres or Mongo or whatever you're using. Now, Redis query engine is written in C, 63,000 lines of C code, disregarding benchmarks and tests, so the lines that actually run in production. And Redis has decided that they want to migrate that from C to Rust. The main reason, the main drive being memory safety. They want to improve the stability of the software that they're distributing to users. They have done this before, by the way. In 2020, they rewrote another extension, Redis JSON, which provides native support for the JSON data type over from C to Rust. In that case, they did a from-scratch rewrite. Started a new project called Redis JSON 2, nicely. Rewrote the functionality in Rust, reached feature parity, and swapped it over. At the point of the swap, it was roughly 1,000 lines of Rust, so relatively a small project, like a single large C module. This strategy doesn't work for Redis query engine. A is much larger, 63,000 lines is a lot more than 1,000, and B, it's actively being worked on. So you have multiple teams of full-time software engineers, adding features, fixing bugs, improving performance on a daily basis. If you were to rewrite from scratch, you would be chasing a moving target, significantly increasing the risk that the project may never land. So we chose a different strategy. We chose to rewrite in place, incrementally. The way this works is you look at the project as a module graph. So you have every single box in here is a C header file and a C module, and each arrow is a dependency between modules. You look at this graph, and you look for leaves, so modules that have no other dependencies. You then go and rewrite those as a Rust module. You will have a pure Rust module that implements the functionality, and then a Rust FFI layer that makes it so that C and Rust can interoperate, and the rest of the code base can consume your new Rust module. And that makes it so that the rest of the code base can keep working as it is, usually consuming a C header file generated by C bindgen, and you go module by module. So you start by AAC, AD is another leaf. Now, AA, it only depends on Rust code. You rewrite AA over to Rust. And you do this over and over and over again, and eventually the entire graph is orange. Now, reality is a bit messier. This is the module graph of the project we're working on, snapshotted in March. So you can still isolate, a few leaves here and there at the boundaries, but once you get to the core, yes, it's a bit complicated, it's a bit cyclic. So it more or less looks more realistically like this. So you will find the modules that are more suitable for being ported, you will rewrite those into Rust, but you'll still keep depending on some C functionality, and over time, as the migration progresses, you'll try to prune those away and kind of increase the area of safety where the borrow checker can actually enforce its invariance. And if you look at it from this perspective, boxes and arrows is very easy. Rewrite that, rewrite that, rewrite that, rewrite that, and eventually the project is finished. The reality is that modules may use idioms or have constraints and requirements that don't necessarily port easily to Rust. They don't port easily to safe Rust in particular. So I'm going to walk you through a specific case study, which is one of the first modules we ported, a TrieMap, a data structure, showing you the kind of challenges you may run. So a TrieMap is, as the name implies, a map. So it's a way to associate keys to values. In this example, the keys are strings, cool, biker, biz, and bike, and the values are emojis. You can think of a TrieMap as a hash map, where the keys are sequences of bytes, or generally sequences, and the values are generic payload. Could be a pointer, could be a string, could be a number, whatever you need. A TrieMap is something you use when you're looking for specific properties. In particular, you're looking for optimized prefix searches, so find me all the keys that start with a certain segment, as well as key compression, so where your keys share a lot of prefixes. This may happen a lot in natural language or URLs, for example. That makes it so that the TrieMap is very compact in memory, and this is desirable if you're doing a database, as we're doing here. Now, a TrieMap is stored in memory as a tree-like data structure. So you have nodes and edges. And those nodes and edges track three types of information. You have a label, which is associated to each node, so it's a little sequence of bytes. We don't necessarily assume that it's UTF-8. Then you have children, so sequence of pointers to the nodes that are child of your current node. And then you have a payload, which may or may not be there. The keys are stored spread across different nodes. So for example, biker, from the example before, you reconstruct that by concatenating the labels of all the nodes that lead to the payload. So bi plus ke plus r. That's how you get biker. And that's how you get all the properties we were talking about before, like the key compression. How does the C module that we're trying to rewrite actually store this node? It stores it like this. I'll give you 2 seconds to look at it. Now, I haven't done a lot of C, so the first time I looked at this, I was a bit confused, especially by the comments. It's like, there's a bunch of fields, and now there's a bunch more fields, but they're not actually there. What does that mean? Well, I did a nice diagram, which is now rendering weird in terms of colors. But anyway, you have 3 important information in this memory layout. Number 1 is a single heap allocation. All the data that belongs to a node is stored contiguously in a single slab of memory. Number 2, some of these fields have variable lengths and variable offsets. So you don't know how long the label for a specific node is until you're looking at a specific label. You don't know how many children it's going to have until you're trying to create it. So that makes it so that the layout and the size of the allocation is only known at runtime. And number 3, the layout is packed, which means there is no padding between fields, which means that some fields may be misaligned. So for example, the children pointers, which are 8 aligned, in this specific example, are not 8 aligned. They start at 20. And that's because of the length of the label and the number of children for this specific node. Trying to port this over to Rust is a bit challenging. As far as I'm aware, there's no way to do it in safe Rust. The module is fairly large, so it's 1,000 lines of code. So we decided to do something different. Rather than trying to approach a one-to-one port, from the get-go, and try to tackle both the performance and the memory usage and the correctness at once, we decided to establish a baseline. In this context, a baseline is a functional equivalent implementation, so same API, it passes the same tests, but is intentionally simplified in the way it's implemented. So our baseline definition for a node, you can see there, it has some of the optimizations of the original. So we have the first byte of the child inlined into the parent. We're using vectors which are low memory, so they have smaller capacity, U16, because that's enough in this case. But other than that, we're not trying to emulate that compact layout. We're not trying to emulate the single heap allocation. It's reasonable to assume, and spoiler, we will see later, that this is going to be slower, too slow to actually be viable. But what this will allow us to do is to achieve a bunch of objectives. Number 1, by actually implementing a TrieMap, something that I don't usually do on a Wednesday, you understand how that works. And that understanding will lower the cognitive load that you have to manage when you then try to do the optimizations. So this is a kind of non-tangible but real benefit of going through a POC stage. Number 2, since we're doing something that is functionally equivalent, we can also make it so that it has exactly the same API, which is going to be very similar to the original C header file that we're trying to port. So we're going to be writing all our unit tests against that public API. If we throw the baseline away, the tests, they stay with us, so we don't have to rewrite them again. So we know that it is correct. With the same principle, we can also add micro-benchmarks. So Redis Query Engine does have a suite of benchmarks, but they are full system benchmarks. So spin up a database instance, run a bunch of queries, measure throughput, measure usage, latency, etc. It takes a while, like an hour and a half, I think. So it's not the best thing when you're trying to micro-optimize single line of code. You want to have something with a bit of a faster feedback loop. We can write that with micro-benchmarks. We can bench against both the Rust version and the C version, so we can call into the existing C module by FFI. And those micro-benchmarks will still be viable for us once we do the actual faithful port. And you can see, this was something that we did quite well. So the coverage is in the 96%, which is a lot higher than the original 80. And performance is what you would expect. So the C version, you can see in this criterion plot on the left is the fastest, around 20. Then we have our Rust implementation in the middle, which is both slower and has higher variance, which is not nice. And then you can see as a baseline something from crates.io, so the Radix 3 crate. So it's not like our version is rubbish, but it's still not fast enough. It's twice as slow as the target. And the picture, the relative speed or slowdowns are consistent across the different operations that a TrieMap needs to support. So insertions, retrievals, removals, etc. Which means that we are too slow and also too memory hungry. Every time you have something like a low memory back or a VEC, you have metadata. You're tracking capacity, you're tracking length. All these things do add up to roughly twice as much memory usage, which is not good enough. So we're going to do a different version, and this will let the unsafe flow. So this is the layout of the C version, just a refresher. The layout of the first Rust version is going to have a simplifying assumption. We're not going to try to make it packed, because having to deal with misaligned fields is one more complexity. And our assumption is that the memory overhead of alignment can be minimized, and actually we're going to get a speed up by having aligned fields. So we're going to do this. Same fields from a logical perspective, different ordering. So we're going to place them in such a way to create a single padding region, which is right in there. And that padding region is going to be worst case scenario, 7 bytes. Best case scenario is going to be empty. That depends on how long the label and how many children you have. The complexity of doing this in Rust comes from the fact that we don't know at compile time how big the type is. So in Rust lingo, this is a dynamically sized type, a DST. You have been using DSTs every day, slices, trade objects. But defining your own custom DSTs, well, that's a little bit of a less well-supported area. Philosophically, this is the type you want to define. So you have label length, number of children, very normal-looking fields, U16 and U8. And then you have arrays whose length is the value of those fields. Rust type system doesn't support this, probably never will. So what you end up having to do is something a lot more implicit. So you define a stack type, which is going to be a node. That's going to have a pointer to the heap allocation that's going to store the node data. And we're going to have a little phantom data there to tell the type system that, this type is generic. So we have a data payload. On the heap, we're just going to represent the fields which have known at compile time, offset, and sizes. We're going to call that the header of the allocation. So there's going to be the label length and the number of children. All the other fields are going to be implicit. As you can see here, if the colors were like I imagined they were going to be, the blue fields are the one in the header, and the green fields are the ones that are variable. But now, everything we need to do is a lot more complicated. Like normally, if you want to place a type on the heap in Rust, you do box new, and the compiler allocates the right size of the memory, it has the right alignment, places the fields at the right places. Now you got to do all of that yourself. So suppose you want to create a node instance, you got to do the alloc invocation. Now, alloc wants to know the alignment and the size of the memory that you want on the heap. And normally, you would get this for free. Now you need to compute this yourself by hand. Now, luckily enough, alloc does have all the methods you need to kind of compose a struct type field by field. And this will give us exactly the layout of that fantasy Rust definition that I showed you before. You then pass it over to alloc, handle the allocation failure, and you have a bunch of memory on the heap, which is the right size, the right alignment, but it's all garbage. You need to initialize the fields, which does mean that you need to do a bunch of pointer manipulation. Go at the right offset, compute where each of the fields need to be, write them over, copy them over from other slices. This takes a bunch of unsafe and more than a bunch. Roughly at the end of the project, we had 128 unsafe expressions and 21 unsafe private methods, which does require some system to make sure this is correct. Which leads us to the last section, managing unsafe code. The North Star is that we're doing this project to improve memory safety, which means that we need to be sure that we're not introducing memory unsafety back into the project via unsafe Rust code. Now, the simplest way to guarantee this is to make sure that the unsafe is contained. And the simplest way to do that is to make sure that there are no unsafe public methods that the rest of the code base can use. That will make it so that you only need to audit what's inside that module. Now, in the case of a TrieMap, this is easy. TrieMap is like a hash map from an API perspective. So you create, you insert, you retrieve, you remove. All these methods are perfectly safe. But you still have all this unsafety inside that you need to make sure is correct. How do you do it? Well, it's a mixture of different approaches. Number one, you will use tools. Miri is a runtime undefined behavior detector. You can run this in CI. It's going to run your code under a couple of different memory models. And usually, if this doesn't surface any issue, that's a good first sign that your code is doing the right thing. Now, Miri errors can be a bit cryptic, unless you have read the Trie paper. So it's good to also abuse the bug assertions. So sprinkle your code with assertions that will only be run in debug modes and in tests. That will give you better error messages as to what is wrong. Then you also have additional tooling in Clippy. So beyond the default lints, you can enable a couple more lints for unsafe code. In particular, we force every unsafe operation to be in a single unsafe block, and we force every unsafe block to be documented. This allows us to adopt, quite strictly, the structured safety documentation that Jack Vrend described in 3 basic rules of safety hygiene. When you're working with unsafe, there's 2 types of documentation that you'll be writing and reading. On one side, when you define an unsafe function, the documentation needs to state what are the preconditions that must be verified for that unsafe function to be safe to call. Every time you invoke the unsafe function, you need to document that those preconditions are met. These 2 pieces of documentation need to talk to each other. And ideally, you need to be able to put them side to side and make sure that all the preconditions are A, addressed, and B, correct. So to do this, you like to have a numbered list on both sides. Now, you don't get a numbered list in most cases, not even in the standard library, but you get a bulleted list, which is better than nothing. So copy non-overlapping, here's a safety section with 4 bullet points. We want to find those bullet points or more in the safety invocation. And we want to make sure that when we line them up, everything has been properly taken care of. But doing this is very tedious. Like, it forces you to write a lot of safety comments. That is 9 lines for a single unsafe block. Multiply that by 100, it's a lot of lines. So what you can do to make both the code base more difficult to misuse, as well as to reduce toil, is to design unsafe private APIs that layer the kind of unsafe that you're writing. So what you do, you build a hierarchy of abstractions. If you're managing that node, you have a heap allocation. That heap allocation has metadata. So you need to know what the layout is. You need to know where each of the field is in that memory region. We store that in pointer metadata. But pointer metadata, every time you try to use it with a specific pointer, you have to prove by safety comments they are compatible. You're talking about a pointer that has an allocation behind it that obeys what's inside the metadata. So it's easier to create a wrapper type called pointer with metadata that only proves that once a construction, so that then you have invariants, which are documented. And you can use those invariants to verify some of those preconditions internally, so that the preconditions that you expose to the rest of the code base are a lot simpler. In this case, we're still calling copy non-overlapping when initializing the children first bytes array, but some of the preconditions in that safety section, like the stuff that the allocation is from the global allocator, there is a single contiguous memory region, that the offset operation won't overflow the limits of the memory, we know we can prove just by the invariance of the struct that these 2 fields belong to. So what we expose to the caller is a lot more semantic. It's basically, don't write more elements than the space we have. Make sure that you are the only one who has access to this buffer. And yeah, it's a non-overlapping copy, so the 2 things shouldn't overlap. That's pretty much it. So a lot simpler to reason about, a lot simpler to reason about correctly. Few parting thoughts before we gave space to questions. Now, this is the before and after. So we had 1,000 lines of C code with 80% line coverage and no microbenches. We converted that into 1.9 thousand lines of Rust, so more verbose. Of this, only roughly less than 10% is unsafe. So we have reduced the scope of the code that needs to be audited. And we've also reduced the opportunity for unsafe elsewhere in the code base. We've improved test coverage, and now we have micro benchmarks, which leads to a broader point. Like when you're doing a rewrite, you're never just doing a rewrite. You're also just paying off that debt, making sure that the code is more maintainable, and it's easier going forward to work with that module. And performance-wise, since we mentioned that before, we're faster. We can see this here. Now, the performance is so super scientific because there's some inlining differences when you benchmark via FFI calls, but it's substantial enough to be measurable, that we're actually faster than the original version. And memory-wise, we only use a few percentage points more, so the padding is actually not a problem. So it allows you to also challenge some of the assumptions that those modules were built under at the time when they were built, which is probably 9 years ago or older in this case. And most importantly, it's in prod. Like, this was released in the Redis 8.2 release in August. So if you're running Redis 8.2 and you're using Redis Query Engine, you're running a Rust TrieMap. And as new releases flow out, I think new one should be coming in October, more and more Rust will be coming online. So this is pretty exciting. And I think that's all I had to say to you today, and we have a bunch of time for questions.
I see two questions already, but I'm going to take the opportunity to ask one before everybody else. You talked about memory safety was sort of part of the motivation, but what was the other motivation to rewrite this code from C++ to Rust?
From C to Rust.
Rust.
I would say that's the number one, really.
That's the number one.
Yes.
And why did they want the memory safety then?
Well, you want to reduce crashes at runtime, right? Like your database needs to be reliable. So that's the number one property they care about. And because of the way this code base is architected, there's a lot of iterators and abstractions that are easier to do if you are working with Rust than with C.
Perfect. Okay, I have one here, I have Ansgar, and one over there.
Hi there. Great talk. Thank you.
Thank you.
I'm a very paranoid person. So when I see you saying this, oh yeah, we just put this behind the safe Rust boundary, there's one scenario that I worry about very much, and maybe you can do something to address my fear. If I have a function that takes two parameters, one is a mutable reference to a foo, the other is an immutable reference to a foo, then in Rust, they're guaranteed to not alias. In C, it's perfectly fine for them to alias. Am I right to be afraid about this? Did you encounter some situations like this, or is that something where you think
it's not something I personally encountered.
Mm-hmm.
I don't have much more to say than that.
Okay.
I'm sorry.
Thank you.
You can boldly go there now. So Ansgar, and then I see you over here.
Thanks for the talk, Luca. My question ties in a little bit on what Sabine was already asking. So you're saying like you went for memory safety, so it's a little bit of confidence, a little bit of reliability. Did you also apply some economical KPIs to it? So how much effort did it take you to migrate? And is that worth it from an it's easier to maintain, so we have more developer efficiency, whatnot kind of perspective?
So we're tracking this as we go through the migration project, but it's still early days to establish, mostly because you have to port some foundational modules to get to the point where you can write the new code in Rust, which is the real objective at this point, right? Old code, generally speaking, is rarely the source of bugs, mostly because the worst one usually have been shaken out over the years. Something may hide, in the corners, but we're not quite at the point where we have managed to port the core of the code base. That's what we're working on right now. And then it will be easier to track the bugs in the new features that are written in Rust compared to the bugs in the new features that are written in C. And then, based on the cost on those bugs, it'll be easier to see if this was worth it or not. So it's TBD. Well, let's chat next year.
But do you have an impression how much effort went into migration?
I know numbers as to what effort has gone now, but I think it's too early to share.
Okay. And over here.
Great talk. Thank you. You said memory safety was the main motivation for this project. So I'm curious, as part of the project, has there been a discussion about whether it would be acceptable for something like the map to be a little slower if you can avoid the unsafe in exchange? Yes,
you have room to not necessarily always need to match performance one-to-one, but in the end, no one's like to see, a release note for a database that says, my database is now in Rust and it's 10% slower. You want to be sure that you can regress in some areas, like there are areas that are less performance sensitive than the TrieMap, for example, where it's fine to regress 5 to 10% because that happens in, debug commands, things that are not necessarily on the hot path. But on the hot path, we need to be sure that we are as fast, if not faster. So a couple of percentage points here and there is fine, but other than that, we need to meet the requirements.
Okay, I'm going to go over here because I skipped you last time.
Yeah, you have a framework to, when documenting unsafety, or why code is safe, when you're doing it over a call to an unsafe function, it's quite easy because you have these safety commands that explain what invariants you have to follow. But when using language construct like raw pointers, how do you do to ensure you don't miss any requirements?
Are you referring to the FFI boundary specifically?
Not particular. Yeah, maybe, yeah. But as well when using raw pointers or transforming them to references and so on, you need to... There are invariants that defined by the language.
The moment you use a row pointer,
Yeah.
you will have safety preconditions to verify,
Yeah.
right? So that means that you must have communicated to the caller some of the properties that that row pointers, must obey. So it's not really any different. It's the same. Tedious, but the same.
Thank you. Florian, then Florian, and then.
Bit of a detailed question. You said there was a slide about abuse of debug assertions, like abuse or use. I'm wondering, like, that hints that you think there's a proper solution for doing this and debug assertions are not?
I mean, I would like the error messages that I get out of MIRI to be understandable by someone who has not, really studied the memory model. They could be a lot more approachable, like the compiler error messages are. But sometimes they're a bit complex to troubleshoot. So the debug assertion is more semantic. So a random developer that is running MIRI might not understand what's wrong, but if he sees you try to write 6 elements into a buffer that has capacity 5, that's usually easier to say, oh, well, did something wrong there.
Okay, that makes sense because the core library does actually use debug assertions for precisely the cases you described. So I was surprised about the classification as abuse. So.
No, I mean, it's not abuse. When I say abuse, I mean be liberal, like actually include as many as you want. Like we have, in the pointer metadata struct that I showed on the slide, we actually have debug assertions fields where we track the number of children and the label length so that we can use this information in debug assertions on methods and catch, out of bounds and other issues. That's what I meant. So it was a little bit ironic.
Okay. Then one more, or two more over here.
Thanks, amazing talk. Technically, maybe there's something I missed at the beginning. How did this came to be the way it came to be? So did Redis Labs ask help to Mainmatter to do this job?
Yes.
Okay.
They reached out to us like, we want to do this because business reasons this makes sense to us. Can you guide us in this migration? Like, yes.
Did you have a question? No? Okay. Oh, Till.
So we didn't convince them. They were already convinced. Just need support.
I have a mean, excellent talk. Sorry, I wanted to say that first. Thank you very much. But I have a mean question.
Ooh.
If somebody told you you can double the code size, you have 3 months of budget by what looks to me like extremely competent engineers, you have to provide a Rust API around it, but just do the best you can in C to bring this to a modern standard, to improve the quality. So basically do whatever you did, but keep doing it in C with a Rust API around it. Mm-hmm. Other than the fact that you now know where the unsafe bits are, because you have a language that has a keyword for that, do you still think there would be business value in doing that?
We actually do that, right? If you go back to the initial slides where I showed the not super tidy module graph, it is not viable to port every module at the time you need them. So a lot of the analysis that we do is also refactoring in C. So looking at the C code, make it so that we better understand like the safety requirements and just in general like how ownership flows through the C code. And sometimes we bind the C code with the Rust interface in such a way that we can use it automatically from Rust. And I think there is value into doing that. It all depends on what I call the shape of the module. It's a lot easier to do that with deep modules with narrow interfaces, because then you get the best buck for your investment. So you have a nice, strongly type, you understand how ownership flows, and you have safe porting, 4,000 lines of code, in which case, great. If you have instead shallow modules, where like most of the interface is the module, then you're spending so much time trying to understand how things work that you might just as well port the code. So it's tactical, I would say.
Okay. Thank you. Oh, we've got one more. We'll take one more. But this is that, guys.
I was worried I didn't have enough time, so I rushed through it a little bit.
No, we've got Papa.
Yeah, sorry for this late question. Did you try to use C to Rust or something similar?
No, we didn't.
Short and sweet. Well done, everybody.
Easy answer.
All right. Thank you so much, Luca, for your talk about rebuilding things into Rust from C. And Luca will also be around at lunch.
Yeah, I shall.
To keep answering your questions, keep having this conversation. So thank you, Luca.
Thank you very much.